Hi guys, this is Jeff Lendermon with GoEngineer. I'm a plastics application engineer concentrating with the SOLIDWORKS Plastics Simulation software. Welcome to my webinar, utilizing the plastic simulation software in the part design phase, how it can be used during the entire process from part design validation into the mold design validation, and also into the processing parameters and some of the advanced inputs that are available within the simulation software. So I'll get started now. This is just a brief slide over the SOLIDWORKS Plastics Matrix. SOLIDWORKS Plastics was developed to help users predict and avoid manufacturing defects during the earliest stages of the part and mold design. So this will eliminate your costly mold rework, improve your part quality, and decrease your time to market as well. You'll be able to run complete injection molding simulation studies on your part designs, mold tooling layouts, and final mold designs as well. The simulation includes filling, packing, cooling, and warp analysis. So the tools within these help design and verify our gate and runner designs as well as cooling line layouts. Also, with SOLIDWORKS Plastics being fully integrated into the SOLIDWORKS platform, the user has the ability to quickly make changes and rerun analysis to validate the part and mold design prior to production of the injection mold. So during my webinar, I'll go over some basic stuff on the injection molding process, and I'm also going to point out a few of the pain points in the injection molding process and during the part design and mold design phase, and show how SOLIDWORKS Plastics can help with those. So since we're mainly concentrating on the injection molding, there's many methods for manufacturing plastic parts, including blow molding, vacuum forming, extrusion, and rotational molding, but we are just going to concentrate on injection molding. So the basic premise of the process starts with the fill stage. Your solid plastic resin, typically in the form of pellets, is loaded into a hopper. The resin is then heated and turned by a screw, which causes the pellets to melt. So plastic on the inside of the machine barrel would solidify if the screw were to stop rotating. So it's not just specifically the heater bands around the barrel of the screw that melt the plastic, it's also the friction of the rotation of the screw inside the barrel. The next step would be in the pack stage. Pack stage is going to be when the resin begins to cool as soon as it touches the walls of the mold. It causes the plastic to shrink. So in order to reduce the shrinkage, additional molten plastic is forced into the mold under a constant pressure after the fill stage is complete. So this stage continues until the plastic ceases to flow through the gate. Our next step is our cooling stage. So after the pack stage, the plastic continues to cool in the mold until it is cool enough to be ejected. And then finally, the ejection stage, once the part reaches the ejection temperature, it is then ejected from the mold. The part will continue to cool to room temperature outside of the mold. So all of these stages and all of these stages of the process are available in the simulation of the SOLIDWORKS Plastics Simulation software. Even after ejection, in the part continuing to cool to room temperature outside the mold, that's part of the warp analysis. So that's actually, the simulation goes beyond what happens inside the mold. So now just a little bit of basic on part design. One of the key things that you always hear designing a plastic part is maintaining uniform wall thickness. So it's the single best design element you can incorporate into an injection molded plastic part. So it helps facilitate even material flow during the injection portion of the molding cycle, and it promotes uniform cooling, which minimizes your warp, twist, and other part feature distortions. So one of the key things we look at in our molded part design, and if you have non-uniform walls, you end up with sink marks. So the sink marks are caused by thick wall sections. The sinking will occur during the cooling process. So if you have very thick wall sections that when the part comes out of the mold, it may look good, but if the inside of the part still has molten material in there, that may sink in, causing the sink during the cooling process. So the sink marks can be predicted with simulations. I'll show you that when we jump over into the software. And minimal sink can be corrected with some processing changes, but large sink areas would require a part design change. Another thing that goes hand in hand with uniform wall thicknesses is avoiding abrupt transition. So if you can't have a completely uniform wall thickness, you'll have a transition from thick to thin. You want to try to keep this as smooth as possible. So if we look at this flow video showing this thick wall section around this earpiece, you see the material wrap around and create this hole down in the bottom. Basically, that's called race tracking. So that happens when the plastic hits the thicker section. It'll actually flow through the thicker section faster than the thin sections, and it causes flow hesitation in other areas. And then molten plastic flowing inside of a mold cavity is always going to take the path of least resistance. So if we were to go in and make a design change, thin out that wall section, and we can watch the video, and it actually changes the way the material flows, and it makes the weld line point up into the top part of the part, where we could vent the air out better at that place. So that's another little plastic part design change. So I've got just a few little gate location general rules. So this is another thing that we like to look at when we're designing a part, is trying to figure out also where a good gate location would be. So the general rule, 1 gate per cavity should be sufficient. What this does is help you avoid undesirable weld lines in the product. If you have multiple gates, you're going to have 2 flow fronts, and at some point those flow fronts come together, and they may cause issues with some visible weld lines that could be not good for visible areas on your part. Also, when possible, inject into the thicker section of the part geometry first, and then let it flow into the thinner parts. If you inject into the thin areas of part, your pressure drop through a thin section will require higher pressure to fill and pack out the thicker section of the part. So it's better to go from thick to thin. And if possible, place your injection location toward the middle of the part geometry. This minimizes your flow length within the cavity of the part. So 2 or more gates per cavity. This is for very large products, so they're needed where flow distance from a single gate would be too long. You could have a large part, very long, with 1 gate in it, but you just can't put the pressure to the plastic and get it to fill the part completely out before your gate freezes off. That's when you'll start to have to add additional gates. Another reason to add 2 gates, you can place a gate on either side of a long cylinder core. It will help prevent core shift. If you're injecting material on one side of a core, it may actually push your core over, and it will no longer be centered in the cavity like it's supposed to be. Also, for round parts, placing 3 or 5 injection locations positioned radially from the center, allowing for a uniform pack, and it also minimizes your oval deformation. So within the SOLIDWORKS Plastics Simulation software, we can actually simulate different gate sizes, and we can analyze the gate size. So what your gate size is going to have effect on is your part filling velocities and pressures, which means a small gate could freeze off and result in a short shot or an underpacked part. Freeze off is when your material solidifies at the gate, stopping the flow into the part. So you want to be sure that your gate sizes are large enough that all the material gets injected and packed out before it freezes off. And there's some tools within the simulation software that I'll show you that help with that as well. Also, a small gate size could cause excessive shear stress within the part, which results in gate blush and or material degradation. So what gate blush is a visual effect that kind of looks like the part is fogging in this area. It's really noticeable on a clear part, so it'll have this foggy tint around the gate area. Too large of a gate may not freeze off at a proper point, resulting in an underpacked part due to backflow of the material. So if you make your gate too large, you're not going to be able to pack it out really well, and then when you eject the part, it'll actually allow material to backflow back out of the gate. So now I'll jump over into the software, and we'll look at some of these tools, concentrating on part design and the simulation. So with SOLIDWORKS Plastics, the user interface is very familiar to you, so it's easy to learn. I typically always use the feature manager tree down the side when I'm creating my analysis. You can also use the wizard and it kind of walks you step by step through the process. So this is a basic part that we're going to look at and look at some of the design flaws within this part by analyzing it utilizing the simulation software. In a simulation, the first step is going to be to mesh the model. I've got all my models pre-meshed, and I also have a gate location picked out as well. I used a solid mesh on this part, and if you look at my gate location when I specified my injection point, you can actually, it's just picking a node. So that is just one way you can assign a gate. The other thing we look at when we select our polymers, we're going to analyze our part. One of the important things we want to look at is our polymer material parameters. In this, we can look at our melt temperatures, our ejection temperatures, and glass transition temperature. Those are important to look at. And also, as I pointed out with the gate blush, we also look at our maximum shear stress or maximum shear rate for materials there as well. Another tool, we talked about not uniform wall thickness. We can look at the nominal wall thickness on a part, and it goes through and analyzes. It gives you basically an average wall thickness and also gives you your minimum and maximum, so the greater area. So obviously this area here is very thick, and we'll see the effect it has on our product. So once you've got the part meshed, you've got your material selected, and you've got your injection point selected, you can run an analysis at this point. So you do not have to go in and put all the fill settings and pack settings in just to see a basic flow analysis. So I'll open up the flow analysis. And the thing we want to concentrate on this at this point is our sink marks. So it shows the area where you have the greater amount of sink in these thick sections. So one thing I really like about the simulation software, after you've created a study, you can duplicate that study. So if you create a duplicate study, it starts a new configuration within SolidWorks. So it allows you to go in and make changes to your part geometry right within SolidWorks. It turns into a configuration, and you can run a new study on that configuration. So it's all tied together in one file. So in this case, I went in, I cored out both sides of the part in that thick section. My injection location is specified the same way. All the material settings, when you duplicate the study, everything's copied over to all of your mesh refinements, everything, it's all copied over. So it's easy to do multiple what-if situations. So now if we go in and look, I can look at sink marks again on this part, and we see the area that I was concentrating on getting the sink marks out of that just by coring the part out. Of course, you're going to make the part lighter. It'll actually reduce your cycle time. I can flip back over and show that. If we look at the cooling time on this part, 13.5 seconds basically for the part to cool to the ejection point. I'm going to jump back over to the other one really quick. And we'll look at the cooling time on it with that thick wall section, 159 seconds. So right there, that's a huge decrease in cooling time, a lot faster cycle. You'll get your parts out a whole lot quicker. So one of the better practices I like to do with the gates, with my injection points, prior to having solid model runner and gate and everything in there, I like to create a split line on a face. So what that does is give me an area where when I mesh the part, I can do mesh refinement around that area, and also gives me a better area to evaluate for shear stress and all of that on the part. So basically, this is the same model. I did another duplicate study, but I added that the split line, refined my mesh around that area. We'll go and look at the flow result on this part. On this one, I want to concentrate and look at the shear stress in the gate area. So the highest shear stress is 0.59 MPa, and it's basically behind this area on the gate. So that's on high shear stress in that area on the part. And if that's above what our maximum shear stress for this material is, it'll cause that gate blush. So I can flip back over. Let's look at the material that's selected on this model. And our maximum shear stress 0.495. So we're over that. It was 0.59. So one of the things you can do in your analysis for the design, we'll go back in. I'll load a new study. This one I wanted to reduce the shear rate on the part. So one way we can do that is by enlarging our gate size. So I went in, made that gate area split line larger, didn't remesh the model since I made a geometric change to my model. You have to go in and remesh the model. I reset up my injection location, went back in and run my flow. We'll open the flow results again here. So once again, I'll go look at the shear stress at the end of fill, and now with a little bit larger gate, we've dropped from the 0.59 down to 0.16. So we have a whole lot better shear stress rating through the part, less likely to degrade the material and less likely to have the gate blush. So that's another option we have to look for during the design phase and looking at your gate sizes and locations. The other options we have to look at during the design phase with just the simple flow simulation, we can look at weld lines and air traps in our model as well. So weld lines are the black lines, so it'll show where a flow front comes together. So if you're flowing around a core, or your material flows around the thick section into a thin section, and then the air traps are basically these little magenta balls that show up on the part that show areas where you would need to add venting. So when the air traps are going to be on the model all the time, you just want to make sure that where you place your gate puts the air traps in areas where the flow of the material where you can actually vent to the mold. So you want to have air traps that are near where a parting line would be. So in that area, or near the end of a face where you could vent through an ejector pin or add vent pins into a mold that way. So those are the basics on how to, just some basic things we look at for part design with the analysis. Now we'll look at some of the things, some of the capabilities with the plastics analysis that have to deal with during the mold design phase of your part. So during your mold design phase, SOLIDWORKS, the plastics analysis has tools that will analyze and develop a runner system for the mold. The gate and runner simulation tools are easy to use. They'll allow you to specify a runner path with simple 2D or 3D sketches. And the analysis includes a powerful analysis, which is a runner balancing tool. So it balances your runner system for a family mold. and this is a key importance. Having a balanced runner system is key when designing a multi-cavity mold. It equalizes your part filling times and pressures, which will result in a more efficient cycle time and a wider processing window. So if you do not have a balanced runner system, the one part fills sooner than the other part fills, you're going to have put a whole lot more pressure into one part, which will put in more residual stress and cause more warpage. And your other part, a lot of times, may have issues packing out, and you may have sink marks on that part. I've seen unbalanced runner systems where one of the parts flashing and the other part has sink marks just because it was not balanced. If you look down on the bottom right, the little window that says SolidWorks, the runner balancing analysis is completed. So, but this is the report. It pops up on your screen when the runner is not balanced. So in this initial one, I made all the runners all the same size, gates were all the same size, and then it went through the optimization. So it tells you the difference in time and the difference in pressure between your parts. So it went from a 0.369 second difference to a 0.038 second difference. So a whole lot more consistent on time, and also the pressure dropped down to 8 MPa versus 40 MPa, which is quite great. So also when we're working on mold design, running a cooling analysis will help determine your waterline layouts and get the best waterline layout. So you can go through and analyze your layout for water lines, find your hot spots on your mold, and everything. So as we know, cooling occurs throughout your entire molding process from the fill stage through ejection. So your rate of cooling will have a significant effect on your part dimensions and is a factor in your part defects. So our key is to cool the part uniformly. It'll reduce residual stress. It also minimizes the risk of warpage and cracking. The system is going to assume that all of the mold wall temperatures are uniform throughout the process. So you'll have, it's almost like a perfect world scenario with mold cooling, which we know in injection molding, running your water lines through there, your flow rates, your water temperatures, materials, all of that affect the mold temperature all around your part. Your thicker wall sections will generate more heat, so you have to make sure you run cooling through there. So by running it through the analysis software, you can look at your cooling lines and find hot spots in the mold, areas where you need to improve the cooling, maybe run a baffle or bubbler into those areas, which we also have those available as well. So when we set up a cooling analysis, there's 4 different solvers within SolidWorks Plastics. The flow field, which is the highest priority, it's the most accurate, it's fully 3D CFD approach. You can select multiple inlets and outlets, and it also looks for turbulent flow. So if you look at the bottom of this slide, it actually shows you during the solve process, right at the beginning of it, it shows you an inlet Reynolds number. What it's looking for is a number greater than 4,000, which in the injection molding industry is what creates a turbulent flow rate. So that's the most efficient flow rate that will remove the heat from your mold going through your water lines. The second solver is cool pipe. It's the second most accurate. You can utilize water channels created from 2D sketches, and you have single inlets and outlets. And the third one is a cool entrance. So basically it solves your heat transfer by determining the convection load from the inlet flow rate and temperature of coolant. It's not as accurate. It's a little quicker. It may be good for looking at first run base simulations. Typically I always use the cool pipe or flow field. And then the last one is a mold wall temperature. You can assign a mold wall temperature to certain areas on the part. So if you know you have an area in the mold that's hot, you can assign a mold wall temperature at that area. So there's no cooling lines that are solved for. You're just assigning a constant temperature to that area. So now I'll jump back over into SolidWorks Plastics, and we'll look at, we've added 2 more parts to our model. we've got the first one we've done the design, so we've run everything else through. Now we're trying to lay out a mold, and we want to analyze the runner system and run a runner balancing on the system. I can create 2D or 3D sketches. We go in and mesh the model, and during the mesh phase, we can tell it we're going to design channels. If we're doing a shell mesh, we can also go in and look at our channel design here. So in this case, what we do, we see we can select cooling channel or runner. In this case, we're going to do a runner. And basically, you just select the different sketch segments. So each leg of your runner, each time it turns or each time it branches off, it's a different sketch segment. So you can assign the diameters to each sketch segment. So in this case, like my sprue, you go in and assign the top diameter, and you can actually specify the draft angle and how much draft is there as well. So I've gone through, created my runner system, ran my initial flow analysis, and we'll look at the flow on this part. We can watch the part on the left, and I can back off to a point, and we see at this point, this part's still full, already full. This part's just filling out. So there's a huge difference in the part filling. So what that does when we look at our pressure at end of fill, we look at the difference in pressures through all the parts. So this one's going to have a lot greater pressure going to the part. It's possibly going to be overpacked. A lot of residual stress within the part as well. And this one, the last fill, has a whole lot less pressure. So, and it's also one of the thickest wall sections. If we look at sink marks, we can look at areas where there'll probably be really great sink marks here. So if you have a huge difference in flow rate, you'll have a lot of difficulty getting this part filled and packed out enough without overpacking that part. So if I go and open the runner balancing tool, I can show the thickness distributions. Let me hide the sketch. So they're kind of hard to see, but everything I've modeled, these are all 6 millimeter legs of the runner. And what I can go in and put in is the maximum runner diameter, my minimum diameter runner, and then my maximum diameter and minimum diameter of your inlet. So that's your gate location. And then the number of iterations. So I ran mine at 20. If I click calculate, what it does, it goes through all the iterations and tries different diameters of the runner until it comes to one that it balances out. And remember, I showed you the report on the slide that balanced out. So now I'll open up the balanced configuration of my runner, and we can see what it did with the runner system. We've got a lot larger runner system on this side to help it fill out quicker, and also change those as well. So now if we look at our fill time plot, we look at the ends of the parts, they're all similar in color, so they fill very close at the same time. We can also look at our pressure differences as well. So if you look at the gradient of colors, they all look pretty even and equal with the amount of pressure. Your highest pressure point in the mold is going to be at the tip of your runner system, so at the end of your sprue. So this is a whole lot more balanced runner. It's definitely going to help your process and everything. So after I've run the analysis and got the balanced runner, typically what I do, I'll go in and remodel my runner up as a solid and rerun the analysis. So in this case, I've run the solid model. Another thing we look at in the mold design is, remember we looked at air traps. We can actually run a vent study when we set up the model. And we can actually add spots on the mold where you select different nodes at areas where the part's going to be vented I think I selected a few of them, and just selecting a few of them actually allows you to run in the fill settings. We tell it that we're going to run event analysis, so we can check off venting analysis, your cavity initial air pressure and initial air temperature. Those are kind of default settings. You can change those to what you want them to be. But when we look at our flow results, the venting pressure on the tool. So look for different areas. So these have much greater venting pressure. It's in an area down at the bottom of a cavity. You definitely have to vent around that area a lot to prevent burning of the part. So these are high pressure areas where it's trying to push the air out of the mold. If you're not vented well, it's going to actually either cause a short shot in that area because the material can't fill it, or it may just create burn marks on the end of the part, which is basically the air is combusting and burning your plastic at that area. So after I've got my modeled runner system in place, I can add a cooling analysis. So we'll look at the cooling analysis on this part, and I'll show you where you can measure your temperatures and analyze your cooling system. So once again, our cooling system are designed off of sketches. So during the meshing phase, you specify that you can create a simulated mold, and you can also specify sketches that you're going to utilize for different runner layouts. So they're specified the same way we did in the runner system. So once I open my results on this part, I want to look at my mold temperature at end of cooling. So this is showing the mold wall temperature in the area of the model. We can always use the measure tool within SolidWorks. It gives you these 3 boxes in SolidWorks Plastics, so it gives us a temperature at that node in that area at 48 degrees Celsius. I can select a different spot on the part model as well as 33, so it's a different, and it gives us our difference in temperature in this magenta box. So we want to try to maintain uniform cooling. This is a tool we can use to analyze that. So we may have to look at putting beryllium copper cores in there, some type of material that actually transfer the heat out better, maybe run a bubbler or a baffle system, which you can also simulate in the cooling process as well. So now I'll get into the process settings. We'll do this without going into the software on it. SolidWorks Plastics allows for our process setting changes in our setup of an analysis. So it's very helpful when optimizing or troubleshooting the injection molding process. So during our selection of our filling stage, we've got basic settings of our filling time, the melt temperature, the mold temperature. The melt temperature and your mold temperatures come from the material database, so they're automatically in there as default. These you can change. Your filling time you can also change as well. So if you're analyzing an existing process and you know the fill time is set at this on the machine, you can go in and set that as well. Your injection pressure limit is the injection pressure, the plastic pressure limit on your machine. So you can always put in your high limit on your machine that you know you're going to be molded in, and that also you've got a clamp force limit in tons. So if you know that mold is in a specific machine, you can put that clamp force limit in there. You'll also get warnings during your process that you've exceeded the clamp force. So under advanced settings, if we look down here, we've got the flow pack switch point. So if you're running a scientific molding process, which typically what you do in that process is you're switching from your flow to pack around 95 to 98% of full volume, which makes up for differences in viscosity from lot to lot of material. And also we've got the flow rate profile settings. So the flow profile I have up there, if you're running a multi-stage flow profile on a part, you can also go in and simulate that over time or over volume control as well. The same with the packing stage. You've got pressure holding time, pure cooling time, and pressure profile settings as well. So all of those are also available to optimize your injection molding process. Cool settings, basic settings, your melt temperature, air temperature, your minimum coolant temperature, average coolant flow rates, so, and your mold open time. So when you're running Cool Study, having the mold open time calculated into the process also helps make your cooling analysis more accurate. And then finally, our warp settings. So basically there's only two settings. You're setting your ambient temperature, which is the temperature at which the part is cooling outside the machine, and then your gravity downward direction is what you set for. That's basically how your part's sitting on the table as it cools. That is where I'm going to end this webinar for today. Thank you. This has been Jeff Lendermon with GoEngineer. Have a great day.